Hi, I'm Michael Davies. I'm a research analyst with Green Econometrics. I'm here today to follow up on our segments on EV charging and the impact on the grid. From part one, we talked about EV charging and the benefits or the economics of EV over conventional vehicles and found that roughly a 70% savings over internal combustion engine, namely a gas-powered vehicle. From part two, we got into the impact on the grid due to the energy endpoints, namely DC fast charge. DC direct current fast charge is practical because when you're on the road, you want to be in and out of a charging facility within 20 minutes or so. And DC fast charging is the standard that will enable you to get in and out quickly. So the DC fast charge platform itself is quite demanding in terms of capacity. It's essentially, a commercial building in a box. So these are distributed over long distance transmission lines, which makes it complex to manage the grid itself. Namely keeping the frequency, voltage, and reactive power in check. So to further explore this segment here is dealing with the EV charging systems, namely the National Electric Vehicle Infrastructure Plan and the call for the installation of 500,000 EV charging stalls across the country along the interstate system. This is funded by a bipartisan bill, $5 billion, and it's due to take place in the fall. And so to get a better understanding of the implications of the requirements under the National EV Infrastructure Plan, I'll bring together some slides just to set some perspective there. Namely, though, let's look at it in terms of some takeaways. And with that, what we found is essentially a 7 to 15% additional capacity call on the grid itself that has to be supplemented with additional energy resources. Hopefully renewable energies will play an important role in that, but we'll see from some of the findings that there's some constraints on how far renewables will go. And again, as I reiterate, the importance of energy storage and distributed energy resources to really provide a foundation for the resiliency and reliability of the grid. So with this slide here, we're looking at consumption. Now, consumption is over the course, and if we look at the Energy Information Administration's data on the grid itself, we see that there's over 4,000 billion kilowatt hours of energy used, and it's broken down between industrial, residential, commercial. So what I've done for illustrative purposes is highlight commercial in the light blue. We also have electric vehicle in the dark blue. The green and the gray represent data centers and crypto mining. We can see currently that data centers and crypto actually consume a larger portion of energy than do electric vehicles. And that's because the electric vehicles are roughly less than 1% of the market, or the vehicles on the road. But as electric vehicles comprise a larger share of the vehicles on the road, once we hit that breaking point of 50%, which could be within the next 10 years, there is a significant portion of that energy which will be consumed by electric vehicles. And so while this may not be that large of an impact currently, the National Electric Infrastructure Plan it may change that quite dramatically. So to better understand those implications, let's take a look at the difference between demand and consumption. So your utility bill for a typical business or commercial facility is represented mainly, that is, by your demand cost and your consumption cost. Your consumption costs are roughly measured by your kilowatt hours of usage over the course of a month, whereas your demand costs are those in just the peak demand measured in a 15-minute interval. Whatever that peak demand is what you're going to be billed at, and that's measured in your kilowatts. And so why is that kilowatt important? Because that's the call or the pull on the capacity of the grid to meet that demand. And that expansion of demand is what's critical to support the grid. So to take that a step further, let's look at the capacity of the grid itself, and what is the actual ability of the U.S. grid to support a call for power. And again, the Energy Information Administration provides some data, and we see that roughly 1.1 billion kilowatts are available to support the capacity of the grid. Now, if we go back to the National Electric Vehicle Infrastructure Plan, they were calling for 500,000 stalls, roughly each stall capable of supporting 150 kW. And so the minimum here across that is that the grid is going to be required to support an additional 7% of the capacity to address the EV market. Now, it also calls for support of the combined charge system, the CCS, for the EV charging, and that has the capability of supporting stalls up to 350 kW. So if that's the direction it takes, that would represent around a 15% additional capacity to the grid to support EV charging. And the reason why that is important, obviously, is how are we going to provide power to meet that additional demand? Again, if we look at crypto and data centers, they're negligible in the terms of that total pull or that total demand, because they're normally running 24/7. So it's not just immediate pull to meet the capacity requirements. It's a steady flow, and obviously they'll be growing because of their importance as well. But it's the EV charging which has the greatest impact on the grid itself. So if we take a step back and say, all right, so how far can renewable energy, mainly wind and solar, provide? We have to take certain steps into consideration, namely the fact that solar currently, the efficiency is around 15 watts per square foot. So what does that mean? So for the National EV Infrastructure Plan, we see that a typical location is going to have a minimum of 600 kW. 600 kilowatts is a lot of power to provide. So in reference to solar, to support 600 kW, you would need a footprint of solar roughly about an acre in size. So that is quite substantial, which will limit the viability and feasibility of getting solar around every EV charging location. Again, it calls us back to the fact that energy storage is crucial to support this rollout, to support this plan. And with that, we see that distributed energy resources play just as critical role in meeting that demand. Thank you.